I realized I should have provided some practice with stereocenters being present. So before we move on to the next aspect of the SN2 reaction, I wanted to take a second to just show you some examples of SN2 reactions where there are stereocenters. I mean, we talked about this before, but let's go ahead and bring it up again. Let's say we've got something like this. And we're going to react it with the azide, which was the N3 nucleophile that we talked about last time. And we'll use just some appropriate solvent. Okay, so what we have here is a chiral molecule that is our electrophile. So we have not only one, but two stereocenters here and here, but it's the stereocenter with the halogen present that will only be affected by the SN2 reactions. So as N3 comes and adds to the carbon containing the iodine and pushes off that iodine, we can redraw the product with the exact same arrangement and connectivity, but we're going to replace the dash to the iodine with a wedge to N3, our nucleophile. So only the CX stereocenter inverts. Now, it's true that reaction went through backside attack with inversion of to provide inversion of configuration through that trigonal bipyramidal transition state that we went over through the previous lectures. But recall that I said we didn't need to go to all that work as long as we just recognize that if we keep the orientation of the molecules the same, all we have to do is flip the wedge and the dash, and conversely, in this case, the dash to the wedge. Okay, let's change things slightly. Let's say that I've got my molecules sort of flipped around. So instead of having the stereocenter on the electrophile, the stereocenter is now on the nucleophile. So we have two stereocenters. This is our nucleophile. It does not have the halogen atom. Rather, the electrophile has the leaving group, which is the halogen atom, the delta plus and the delta minus. Okay, so with that assessment, now we recognize that the oxygen has the negative charge. It's going to be attracted to the delta plus carbon atom, and that's going to force pushing off the bromine atom to give rise to a new bond. Now, what's happened is the oxygen did the attacking, and everything that was attached to the oxygen comes along for the ride. That includes the stereocenters that it's attached to, or the stereocenters in the molecule that it's attached to. They are not affected. They do not undergo inversion of configuration. Recall that only the CX stereocenter inverts. That's right here. In the lower example, the CX, where X, just in case this needs a reminder, the halogen now was on an achiral molecule, and so we didn't have to worry about the ramifications of inverting the tetrahedral geometry because we were achiral, so it didn't matter. We were going to get the, we have 3 hydrogens attached to the carbon that's attached to the leaving group. We don't have to worry about inversion of configuration. So my point is, pay attention only to the carbon halogen bond when you undergo inversion of configuration. Okay, so let's do a few more examples. So let's react this with, and I'm just going to kind of draw the nucleophile. Let's keep the nucleophile the same in every case. So we're going to use OCH3 minus as the nucleophile in every case. We have wedges and dashes in these various molecules. The first thing I want to recognize about the first example is that the molecule is actually achiral. It has a plane of symmetry. So because we're achiral, inversion of configuration doesn't happen because there is no absolute configuration. You still could, and it's no issue. If you want to go ahead and draw the product after substitution where the OCH3 is connected as a dash. You could draw it as a dash or a wedge or a straight line in this case, because the electrophile, the haloalkane, is not chiral. They're all the same structure. There is no stereocenter present. So you could draw the dash or wedge in this case, because the molecule is achiral. Okay, now that's not true in the case of the second example. The second example has a stereocenter at this position. So when the negative charge attacks the carbon with the iodine present, we need to invert the configuration. The easiest way to do that without transition state analysis is to replace the iodine with the OCH3 and then invert the stereocenter from being a dash to a wedge, but otherwise keeping the arrangement of all of the atoms the same. Now in this next example, the dot is not at a stereocenter. The stereocenter is present, but that's not part of the halogen atom, and so we don't invert it. We only invert the CX stereocenter, that carbon being directly attached to the stereocenter. Okay, so that is just a quick rundown of some examples with stereocenters present.